Okay, today we're going to talk about logical equivalence and tautologies and contradictions, and this is all going to involve truth tables. Okay, so let me write a definition for you here. Two statements are logically equivalent if they always have the same truth values. Okay. Now, what do I mean by always have the same truth values? You might think, well, don't they have the same truth value or they don't? What do you mean by always? What I mean is this. Consider a statement that's made up of a bunch of smaller statements. Like here's an example. Look at these two statements. The negation of P and Q and the negation of P or the negation of Q. Whoops, that's not a Q. Okay, now that statement, is it true or is it false? That all depends upon P and Q being true or false, right? Same thing here. Is that true or false? That all depends upon P and upon Q being true or false. Okay? But when this one's true, you will see that this is also true. And vice versa. And when the first one's false, the second one's false, and vice versa. You'll see that they always have the same truth value as each other. So those two statements are logically equivalent, and we recognize that by putting an equal sign is how it is in the textbook. Most books for logical equivalence use a 3-bar equal sign like that. Okay? So let me show you how we show that those are logically equivalent. What we do is we make a truth table. And in that truth table, I make sure I have enough room to do both of those. Okay, now I'm going to build this truth table up. It's going to be somewhat of a big truth table, not huge, but somewhat big. So let's start by putting, first of all, our two variables, which are P and Q. Okay, and let's write down the different possibilities of truth and falsity. So we might have both true, P true and Q false, P false and Q true, or both false. Those are the only 4 possible combinations. Okay, now I want to build up to this. So therefore, let's write a column for the conjunction of P and Q. And then we will negate that. I understand you could probably do that all at once. But people who are in the habit of trying to do it all at once are the same people that make mistakes. Okay, let's go ahead and fill in what we have there so far. Okay, so how does conjunction work? Well, you should know by now that the conjunction of P and Q is true in only one case, and that is when P and Q are both true. So this column should be true, and then false, false, false. So its negation will be false, true, true, true. Okay. Now let's build in that one. So for that one, I'm going to write a column for the negation of P and a column for the negation of Q. And then I'm going to write the disjunction of those two, which would be not P or not Q. So since I started out in the P column writing true, true, false, false, then in its negation column I'll write false, false, true, true. Does it matter what order I wrote them at the beginning? No, it makes no difference. The only thing that matters is that in these columns here, I want to make sure that my trues and falses agree with these columns here. Okay? All right. Now, since my original column for Q said true, false, then my column for the negation of Q should say false, true, false, true. Okay, now let's put those together in a disjunction right here. How do disjunctions work? A disjunction is true if either part is true. It is only false if both parts are false. So it should be false in the first case and true in the others. Okay, now you look at this column for that and this column for that, and you see that they match, which means that those two statements always have the same truth value dependent upon the truth values of the components. Okay? And that's what we mean by logical equivalence, and that's how you show logical equivalence. I mean, there's other ways to show it too, but this is the most straightforward way, is with a truth table. Okay? Let's do another one that's very, very similar. I'll use the same table. I'll just empty it out here. Okay, so this other one is going to be not P or Q is equivalent to not P and, no, yep, that's right, not Q. Okay, let's show that. So we'll make a column for P or Q, and then we will negate it. I need parentheses there. Okay, so the disjunction of P and Q is true as long as either one of P or Q is true. It's only false when they're both false. So the negation would follow this pattern. Okay, now let's build in this one. So let's negate P and negate Q, and then do the conjunction of those two things. Okay, I should have left these two columns here because they're the same as they were for the last example. Okay, and then I have the conjunction of those two things, which is only true if they're both true. Otherwise, it's false. And again, you see that the column for this matches the column for this. So they're logically equivalent. I'm not saying they're both true. I'm not saying they're both false. I'm saying when one is true, the other is true. When one is false, the other is false. Or one of them is true if and only if the other one's true. Okay? And in fact, these two are very famous logical equivalences. Each one is called one of De Morgan's laws. There's a De Morgan's law, well, two of them, De Morgan's laws for set theory, right? Which means that, if you remember these, I think we saw them during chapter 1, that the complement of a union equals the intersection of the complements, and the complement of an intersection equals the union of the complements. Those are called De Morgan's laws in set theory, and these up here are called De Morgan's laws in logic. Okay? On page 52 of the book, you will see these De Morgan's laws along with several of others. There's the contrapositive law, commutative, distributive, and associative laws. I don't want to show them all to you because some of them are homework problems. But let's go ahead and do one of the associative laws, just so we can do another practice. Okay, so here's one of the associative laws. It says P and Q and R is equivalent to P and Q and R. That seems, I think, pretty intuitive. The important thing is to notice that it can actually be proven using a truth table. So I think we're going to need it to be, let's see, I think this should be big enough. Okay, so we got three variables, P, Q, and R, which means there's 8 possible combinations. Let me spread those out more. Let me see if I make this. Whoops. Okay, that's not what I wanted to do. Sorry, let me start over. I want to make it a little bit bigger, just so I don't have to write so small. Okay, so P, Q, and R, those are our 3 variables. It's going to be 8 possible combinations. True. Well, I'm going to do all the P's first. I can do it faster that way, because I have a strategy for that. Okay, there we go. Those are all the possible combinations of truth and falsity. Okay, so let's build up to this. Let's do the conjunction of Q and R. Okay, so I just only need to look at these 2 columns here. If Q and R are both true, the conjunction's true. If one of them's false, the conjunction's false. Okay, there we go. Now I want to form the conjunction of that along with P. So now I just need to look at these two columns. The conjunction is true if they're both true, and false if either one of them is false. So there we go. Okay? All right, now let's build up to this one. So I need P and Q. All right, I just need to look at these two columns. So we should have true, true, and the rest will all be false. And now we're going to do the conjunction of that with R. Which requires me to only look at these two columns. The conjunction of those two. Okay, so in the first row, they're both true, so the conjunction's true. In all of the other rows, one of them's false, so the conjunction is false. This is what you're going to need to do on your homework. That row matches this row. When you do your homework, just, column, sorry. Just circle the two columns. Okay? That shows that those two statements are equivalent. Okay, now I don't want to do this one because I don't want to give it away, but I just want to point out to you that when you have a implication, P implies Q, the converse of that, here, let me write this. I think I've shown this to you before, I'm not positive though. The converse of that is Q implies P. They're converses of each other. It's a two-direction relationship. Okay? Those are not logically equivalent at all. Let's see. The inverse of an implication if you have P implies Q, the inverse is not P implies not Q. Those are not logically equivalent to each other. Okay? Now, last one. If you have P implies Q, the contrapositive of that is not Q implies not P. They're contrapositives of each other. Those two are equivalent, and you'll prove that in your homework. That is equivalent to that. Okay? And we use that a lot in logic. Converses are not equivalent to each other. Inverses are not equivalent to each other, but contrapositives are equivalent to each other. And also here's a point of interest. The converse and inverse of a statement are equivalent to each other. Those two green things are equivalent because look at them. Those two green ones are actually contrapositives of each other. Okay? So an implication is not equivalent to its converse, and an implication is not equivalent to its inverse. But the converse of an implication and the inverse of an implication are equivalent to each other. Okay? And an implication is equivalent to its contrapositive which we use a lot. Okay, now on to the next little topic. Tautologies. A tautology is a statement that is true. You can even throw in the word always true. But I'm going to add to that to explain what I mean by that. What do I mean by always true? What I mean is that it's true regardless of whether its components are true or false. And I'm going to show you a few of these. Okay? So, one is the statement P or not P. That's always true, whether P is true or not. That's very easy to see. The only variable here is P, so it's going to be a very small truth table. Okay, so let's do the negation of that. And then let's do the disjunction of those two. Okay, remember, a disjunction is true if either part is true. So in the first row, P is true, and that makes the disjunction true. In the second row, the negation of P is true, and that makes the disjunction true. So you see that this statement is always true, regardless of whether the two components are true or false. And that's what we call a tautology. Okay, some tautologies are famous and have names. This one is called the law of excluded middle. And you don't see it a lot, but it's crucially important because there's a method of proof called proof by contradiction, and the only reason a proof by contradiction is valid is because of the law of excluded middle. Okay? Here's a couple of other ones. This one is called modus ponens, and it looks like this. P implies Q, and P together, those imply Q. Okay, let me prove that for you. Prove that that statement is always true, regardless of whether P is true and whether Q is true. All right, so let's make a column for P implies Q. What would that look like? That would look like this. Now let's conjoin that with P. What would that column look like? Here they're both true. Here one of them's false. Here one of them's false, and here one of them's false. And now let's do the implication of that implying Q. So I just need to look here and here. Okay, this is the hypothesis. This is the conclusion. So in the first row, the hypothesis and conclusion are both true. So the implication is true. In the other three rows, the hypothesis is false, which means the implication is automatically true. Because the only way an implication is false is if the hypothesis is true and the conclusion is false. So you see that in all possible cases, that's true. So that's a tautology. Okay? There's a partner for modus ponens called modus tollens. Which says P implies Q along with the negation of Q imply the negation of P. I won't go through the proof of that, but you should for practice. It's almost identical to the proof of modus ponens. Very, very similar. Okay? So that's what a tautology is, a statement that's always true. And all you have to do is make the truth table for the statement and show that it's full of T's. Okay? The opposite, if you want to say opposite, of a tautology is a contradiction. And that's a statement that's always false. Okay, so what would be an example of a contradiction? Well, you know, a tautology is one of example is a law of excluded middle, P or not P. If you write P and not P, then you would have a contradiction, which is very easy to see. Do the conjunction of those two. In both cases, one of the two pieces is false, and that makes their conjunction false. So you see that statement is always false. Okay? All right, that's all for today.